would be best if you were to do some examples, and let's start. Alright, would you expect a plastic flow in a structural steel subjected to a particular stress? Alright, this is a symmetry, meaning it's 300 minus 300 and 200 over here. Alright, so with this particular stress, will you experience plastic flow? Alright, if you still remember, if your von Mises is equals to your yield strength, alright, you're somewhat, right, if you are talking about this boundary layer now again, right, if you're exceeding this thing, or you're just at this line, you're starting to yield, alright, but you haven't yield yet. But once you cross this line, once you are larger than the yield strength, then you're going to start to yield. Alright, and therefore in order to do that, we're going to calculate our von Mises. Alright, you just sub in your stuff, but instead of subbing your so-called this equation that we often use when we calculate the von Mises, von Mises, we can actually use a different formula. Alright, it's the primitive one that we have derived the von Mises with, the J2 minus, instead of the degree K, we can say that it's the shear part of the yield strength. Alright, the shear part of the yield strength, or you can call this somewhat the devolteric components. Alright, so therefore we will use this formula to calculate our von Mises. Alright, and we know that this one will actually be a sigma m square, your von Mises square, since we know that y can be any arbitrary function, because this is 0. So yeah, I think you get what I mean already. More details, you can go to l7v1, or you can check it out over here. Otherwise, you can simply use this formula instead. Alright, so put this inside your formula list, right, where this is the important one that you may require. Okay, and this part over here is somewhat your ky square. Alright, and then this part over here is your J2. Alright, given that this one is 1/6, then this one is like this. Alright, so if you multiply by 3, alright, then you will have 3/6, so therefore you have half over here, as you can see, and then this times 3 over here. Alright, and at first they were 0, and then since any arbitrary functions can be represented with 0, alright, therefore we just say that it's a von Mises square in this case. Or you can take note that this is all in terms of square, this is in terms of square, this is in terms of squares, and therefore to some extent it's somewhat like a Pythagoras theorem, x squared plus y squared plus z squared plus w squared, and everything square root, alright, equals to your some vectors. Alright, so normally when you deal with vectors, you'll square them, all the vectors, and then find the overall vectors that can represent all of them. So this is something of that meaning in terms of all the shearing part. Alright, I don't go through in details, you can just watch the video if you're free. So you just apply your own formula, and then you just deal with things. Eventually you'll get over here and over here, sorry. Yeah, and then this is equals to sigma m square. Alright, so you have to square root this whole thing, so it becomes sigma equals to 91 times 10 to the power of 4. You should get like 9.539 times 10 to the power of 2. Okay, and this is another method to calculate your yield strength. Your von Mises. Alright, so 954 MPa is somewhat about 1000 MPa, so yielding would probably occur. Okay, because it's somewhat at the boundary layer already. It's somewhat here. Alright, somewhat here. So therefore, if you starting to load it more, you'll start to deform. Alright, yield more, things like that. Next question is usually assumed that the mean stress, which is the stresses that is acting perpendicular to your plane, or the hydrostatic stress, has no influence on your plastic flow. Alright, and therefore discuss the implication of this assumption for your yield functions and their associated yield surfaces. And then illustrate your answer with reference to a von Mises material, alright, where it's being sheared. Alright, von Mises is being sheared. Alright, and what are the assumptions that breaks down and suggests a corresponding yield function and yield surface. It's like macam, you know. But anyway, let's start. If you know Sij, this is actually your devolteric stress. Alright, I'll not go through into what is devolteric stress. I will assume that you really know devolteric stress, otherwise you just go and watch the video on devolteric stress. So therefore this is some of a matrix. So it's a function with regards to a certain stresses, the devolteric stresses, or the pure shear stresses. Alright, and we choose this shear stresses rather than the sigma ij. This sigma ij itself may be wrong, but deals with the stress state of the system. Maybe your sigma 1, sigma 1, 2, sigma 1, 3, etc., sigma 3, 3, sigma 2, 2. Alright, so this stress state itself just talk about the certain stress state of the system. Alright, or otherwise, if you are strictly speaking, you're talking about the diagonal one, or the principal stresses. If you were to minus sigma, you'll get the principal stresses, sigma 1, sigma 2, and sigma 3. Alright, this principal stresses, alright, has its own invariance if you just check it out. But as you can see, the stress invariance of a principal stress, this whole thing is a principal stress. Alright, don't confuse with this thing. This thing is a stress state. When you minus away sigma and then you find determinant equals to 0, you eventually get this one. And its particular invariance can be calculated using this. Alright, and these are all the normal stresses, or you can otherwise say that they are somewhat linked to the hydrostatic stress, because hydrostatic are all mean stress, or the so-called the stress perpendicular to a particular plane. Alright, so therefore we have the principal stress, a function with regards to the principal stress. This y is just a function, like your yt is equals to your y, things like that, or your xt is equals to x. So in other words, we can say that y certain function of devolteric, we choose devolteric rather than the principal stress, is because the devolteric is a shearing, contributes to shearing, and we know that shearing will deform. The devolteric stress contributes to deformations of your material. Alright, while the principal stress only, or the hydrostatic stress only cause the volume to decrease or increase. That's all. Alright, and therefore its corresponding invariance, if you see, is I. Alright, and the corresponding for devolteric is J. Alright, if you know the J1, J2, J3 for one while, it's over at this side. Should have something plus one more, which I think they have forgot to put it, but it should be like this. So this is in terms of your devolteric stress invariance. And why invariance? Because invariance will always change with regards to whatever sigma 1 and sigma 2 or whatever thing that you have. Alright, so invariance change accordingly to your stresses. Once your stresses change, your invariance will change. So therefore, it is well represented, or is quite legit to actually represent your system more efficiently with your invariance. Alright, because invariance is more efficient to represent stuff. And therefore, for the devolteric, we choose the J. For the principal stress, we choose the I. Alright, but because the J that is contributing the shearing and the deformations, that's why we often use the invariant of the J. And if you still remember the using of the invariant of J's, and then when you somewhat plot a certain stuff, you eventually have this von Mises curve over here. Alright, so that's why when they plot, they often plot in terms of a von of a invariance in a certain sense. Alright, and therefore this explains why we choose J. Alright, now let's talk about the implications of this assumption. Alright, how does this assumption saying that the J itself, when we use, is useful for us to predict the von Mises and things like that. Alright, attempt to explain this may be highly wrong. It's just that this shape is somewhat like a prism or triangle. Alright, and therefore when you apply a certain force over here, the prism shapes itself kind of like resists your pulling. Alright, resists your pulling, and therefore it don't actually yield. Right, some sort of the meaning in there. Alright, for the von Mises, as you can see, is somewhat a cylindrical stuff that when you pull, this surfaces will actually somewhat being pulled out to a certain extent. Alright, so if for example you have a U point over here and then you start to pull it out, when you pull it out, the whole material is going to stretch. Alright, so for example, this is the surface. If you are talking about this surface over here, when you apply a force over here, it may actually cause it to yield, or actually being pulled out like this. Alright, we have actually discussed before. Alright, this whole part will actually yield, and this thing will actually being pulled out in this manner, in this direction. Alright, but for von Mises, I think it's somewhat like this. So when you start to pull, the whole shape will comes in this manner. So this is your surface. At first, this is your surface, alright, it's a straight one. After you pull in this manner, you somewhat have a deformed shape, something like this. Or this your cube, or your whole surfaces may be a bit deformed already, or when it's being pulled in this manner. So it's being stretched into this shape from the square cube to somewhat like a bit different shape, alright, in this manner. Alright, so I know that I explained sucks, but at least something there, alright, because I don't even know how the open-ended cylinder would look like and things like that. But it deals with the J2 minus K square. If you still remember, this is the yield strength criteria, or the von Mises criterion. So this is the equation that I've been using just now to calculate all this stuff over here. It's the same thing, alright. Or we somehow have proved that the assumption for for a U function and their U surfaces is somewhat better, is somewhat good if you're talking about von Mises, because von Mises material yield better than we're talking about the mean or any stresses acting on the perpendicular to the plane. Alright, the plane itself doesn't mean that it's perpendicular to your cube. Alright, it's not this meaning. If you still remember, if I were to take a small cube over here, alright, and enlarge it, maybe I should draw this like this. Alright, and I have a point space over here, alright, with a certain stress. These are all the stresses, the normal stresses. Alright, so this point is in 3D point, so it's represented by a certain vectors to represent a certain 3D point. So when you have a 3D point, these three planes actually react, but it's not as good as the shearing part. Alright, when you pull in this direction, there will also be shearing. Alright, your this part over here may actually shear. Alright, so this shearing actually contributes to more on your movement of your stuff when you start to pull. Alright, and eventually you'll somewhat pull in this manner. Okay? Last question is, what is the circumstances under which your assumption breaks down? It is when under a very high hydrostatic intention only. Alright, so you're gonna somewhat pull. You have certain materials. For example, you have a tool, you have to have a tensile stress that is trying to pull this apart. A long time you're gonna cause yielding also. Right, when you have a very high level of hydrostatic or principal stress. Right, and the corresponding Y is the Grissom type with a cigar shape used. I don't know how it is all about, but yeah, at least you may understand something about the yielding. Alright. Okay, now the last question before we go to another video is that determine whether this yielding is likely to occur in a strain hardening the structural steel with a certain stress tensor over here. So same thing, you apply your J2 and your Ky square, right? Or you can say that we're talking about 3J2 times 3Ky square, so to speak. Alright, we have shown you just now, but anyway, let's continue, and eventually you'll find your von Mises. Alright, you'll find your von Mises that is over here. Alright, von Mises square, and then if you were to bring this square over here, you'll eventually find this thing over here. And if you have to compare to your material is 750 MPa, so therefore it's somewhat safe, no yielding. Alright. The question continues, stating that if all the stresses except sigma 11 are gradually reduced to 0, what will happen to the material? Illustrate your answer with a sketch of the current stress point and the yield surface, noting particularly the final shape and size of the yield surface. Alright, I may be wrong, but let's continue. So what it means is that except this 1000 over here, this rest of the stuff will all becomes 0. Alright, so in the end, what will it be? So therefore, if no yielding has occurred, alright, if you still remember our criterion over here, anything that exceeds your this boundary over here is considered so-called yielding occurs. Alright, so if there's no yielding, this means your current stress state must be inside the yield surface of the stress space diagram. And therefore what I'm drawing is called the stress space diagram, and that you're inside within the yield surface, this particular surface that I'm talking about. Alright, so your system may be somewhat like that only. Alright, or maybe like that whatsoever, but it's still within the surfaces. Alright, and now if all the stresses are reduced except sigma 11, this means that you'll have some sort of a stress state like this, alright, where it's only this portion over here, alright, and when you exceed this particular region, alright, you'll actually start to yield, alright, eventually it touches the yield surface and the plastic flow will occur, so meaning it's yielding, alright, and since the material is strain hardened, your yield surface will somewhat expand. So instead of these surfaces over here, your yield surfaces your criteria may be somewhat larger because of the strain hardening effect. Alright, so you may require more forces to actually elongate your stuff or yield your stuff, things like that. Alright, and the current yield stress will increase because when your strain hardening exists, alright, you're gonna need more forces to pull, right? When you need more forces to pull, this means that you're somewhat reaching your ultimate tensile stress. Alright, and this is why somewhat you have reached the 1000 MPa or somewhat the final yield stress. Alright, which is, if you have to compare, the ultimate stress is over here. Alright, so this is the last point of your yielding. Alright, so therefore once you reach here, eventually it will start to fracture and things like that. And I may be wrong, but at least something there for you to get a feel. If you find that in the future there's something wrong, you just leave a comment or do a new video on this. Alright, therefore this is it for this series, and next video we'll talk about some other stuff. I mean, still talking about exercises, and see you there.